Hello class, and welcome to the video for the Kinematics Equations. Before we get into it, I want you to watch this video about a husband and a wife discussing how far a car would go if it's traveling at a certain speed. Enjoy!
Alright, we're traveling from Logan to Boise, and I just proposed a math question to my beautiful wife, Chelsea. And the question, very difficult to calculate, is if you are traveling 80 miles per hour, how long does it take you to go 80 miles? Okay, what do you think, Chel? Let's go through the process. What do you think?
Well, if I run the mile in about 9 minutes...
Wait, what about the tire turning thing you were talking about? You think that affects it?
Well, I'm just guesstimating probably about... It turns about 400 times in a mile.
That's just guessing calculations?
Yeah, I don't know how you would work that out.
It'd be tough.
Yeah, so... I don't know, because if I run a mile in like 9 minutes, then... I mean, but that's when I'm out of shape. When I'm really in shape at like 7 minutes is when I'm like really in shape. And that takes me a mile. And we're going 80 miles. I'm running at about probably 10 miles per hour, if that.
Yeah.
And that's pretty fast for a human being, I think. But, I mean, it's got to take at least like 58 minutes or something.
58 minutes? It's pretty close.
To go 80 miles.
Do you want to know what the answer is?
What?
Think about 80 miles per hour.
Yeah.
So how long does it take me to go 80 miles if I'm traveling 80 miles per hour?
You are driving faster than a minute a mile.
Yeah, totally.
So I would whack 80 in half, and that's 40. Because, I mean, you're probably going 2 minutes a mile.
Just whack it in half.
Well, it depends on it. I mean, some cars' tires turn faster than others.
Yeah, definitely affects it.
Because, I mean, I think a truck probably is slower because it weighs more.
Mm-hmm.
But I think it also matters if your car's a stick or automatic.
Okay, Chal.
What?
Think about the term miles per hour.
MPH.
MPH. So if I say I'm driving 80 miles per hour, that means I'm going to go 80 miles in an hour.
No, you are not, because you are driving faster than a mile a minute. I can run 1 mile in 7 minutes, and that's a 10. Okay? So, I mean, that's booking it too.
Okay, so if I'm going 60 miles per hour?
Then it'll take about 30 minutes. I would just cut it right in half.
I'm trying to explain the answer, but...
Well, you are not making sense, because I make sense, you do not make sense. My car's tires may be they're kind of a little flat, so they may not move as fast as like a police officer's tires that are full, but
Okay, Chel, the answer?
My tires are turning maybe, I'd say about 400 times per mile.
Okay, I'm going to tell you the answer. You ready for the answer?
No, they gotta be like 1,000.
You ready for the answer? The answer to...
You don't know the answer!
I do know the answer.
You can guesstimate just like I guesstimate.
I'm not guesstimating. I'm using math and science. I'm using my own term. Okay, Chel. The answer to the question, how long does it take me to travel 80 miles if I'm driving 80 miles per hour? The answer is 1 hour. Your guess was close.
So say you drive 60 miles per hour at 60 miles. You want to go 60 miles at 60 miles per hour. Is that an hour?
Yep.
What about 40 miles at 40 miles per hour?
Then you will go 40 miles in 1 hour.
No, you cut that in half. You're going more than a mile a minute. Okay, let's time. Right now, let's time and see. Please stop filming.
Hello ladies and gentlemen, that was a very funny video, wasn't it? In this little unit here, we're going to learn about kinematics. Kinematics. Now, if you hear typing in the background, that is my girlfriend typing, so please ignore her. Alright, now let's define what is kinematics. Basically, kinematics, or I'm making this up on the spot, but kina, I do believe, means to move. So kinematics is things that matter that move. Don't quote me on that because that is completely wrong. You know, get it? Matics as in matters and kina mean moving. Anyways, here's the formal definition of kinematics. Kinematics is the way of describing the motion of objects without describing the causes. You can describe an object's motions in words, mathematically, pictorially, or graphically. And so if you're scratching your head thinking, Mr. Lee, what are you saying? Basically, what that definition means is you see something move and we can describe it moving with numbers. But we just don't know why it started moving. I don't know. Okay? So pause this video right now and actually copy down this table, this little chart here, word for word, because it's a mighty good one in my opinion. Alright, so pause. And we're back. Alright, so hopefully you did pause it, otherwise that little segment would have been a little bit weird. We're just going to go through these symbols one by one, and I'm going to describe them to you one by one. Now, in physics, usually symbols are very self-explanatory. For example, T stands for time. Makes sense because time starts with T. Yeah, good stuff. Acceleration, of course, A. X or Y we're going to use as displacement. V naught. Now you see that X or Y for displacement. Now V naught is initial velocity. Naught is that tiny little O that comes after the V. Now notice how it's not VO, like I'm about to type right here, okay? Look at this, look at this. Uh-oh, don't look at that. I messed up. Alright, look at it now. Okay, notice how it's not VO next to together, okay? It is a V and a O below the V. Okay, that's what we call a subscript. Please make that distinction when you write it, otherwise I'd be very upset. Alright, that stands for initial velocity. Whenever you see that O, it stands for initial. Why didn't they use I? I don't know. But they used O, so let's use O. Next up on the list is a V sub F. V sub F standing for final velocity, and or it could be just represented as V, and G standing for gravity or acceleration due to gravity, which we're going to learn about in just a little bit, and A sub G, acceleration due to gravity. Alright, now notice how none of these are capitalized, and there's a very fine distinction on which variables are capitalized and which are not. These on the list are not capitalized, so please, please, please do not capitalize them. Alright, now there are three major kinematics equations, and at which this point I want you to pause the video and copy them down. Alright, now hopefully you copied them down. If not, that would have been another weird segment. There are three major kinematics equations that we can use to describe the motion in detail when acceleration is constant. That is a key point. Acceleration must be constant. And we're going to learn how to use all three of these equations with a couple of example problems. So whenever I have an example problem, pause it, maybe copy it down, or try it as you go along with me, alright? Number one, kinematics equation number one. In this slide, I just show you how this equation came about. We should know that the acceleration is velocity, change in velocity over change in time. Okay, so that's what we see here. I'm going to change that delta, which we know means final minus initial, F minus O, the F isn't there, over time. And then in this step, all I did was I would multiply both sides with the variable t for time, to get rid of that t in the denominator, to get v minus v naught is equal to a times t. And at that point, I just swung this v sub naught over on the other side by adding v sub naught on both sides to get velocity is equal to v initial plus at On to the example. All right, so here we have a boat. You're in a boat, and you're slowly driving out of the marina because we don't want to create any wakes. All right, because they're sleeping fishes. That was a joke. With a speed of 1.50 meters per second. As soon as it passes the breakwater leading marina, it throttles up and accelerates to 2.40 meters per second squared. Question A. How fast is the boat moving after accelerating for 5 seconds? Now, here we see a table, and I highly encourage you to always start off with the table and write down everything that this problem gave you. Okay, so it gave us the initial velocity 1.50 meters per second, which we see right there. So we're going to write that down. It also gave us the acceleration 2.40 meters per second squared. So we're going to write that down as well. And in the question within itself, it told us that the time was 5 seconds. Okay, right. I'm actually pointing to my screen, but you can't see that. So I'm going to use my mouse so I can show you. Okay, and then on the other side of the chart, write down what this question wants you to find out, and in this case, it's the velocity. Okay, it's the velocity. So, okay, whenever we do these type of problems, always start off with the equation. Okay, now there's a strategy to this, and we'll get there in a second. But because we know that this is the first velocity equation, we're going to use the first velocity equation. Duh. All right. Here we have velocity is equal to v initial plus a times t. Now, v initial is 1.50 meters per second, so we're going to plug that in there. And we know that a, or acceleration, is 2.40 meters per second squared, so we're going to plug that in there. And we know that t is 5 seconds, so we're going to put that in there. Now, we're going to separate each variables with a set of parentheses, okay? No gang signs up in here, all right? With parentheses, alright, and I'll show you exactly what that means. It's gonna look a lot like that, and at that point it's so simple. You're gonna be like, oh my gosh, physics is so easy. Because all you have to do is you have to use your brain and do this by hand. Actually, you don't have to do that. You can get a calculator and figure out what is the final velocity. And if you got 13 meters per second, congratulations, you are one step closer to becoming a physics master. It's true. But please do not forget your units. If you do, you're going to get it marked wrong, and we don't want that. Part B of the same problem. We're going to use kinematic equation number 2. All right, x is equal to x initial plus b initial x, which simply means initial velocity in the x direction times t plus 1/2 at squared. Okay. In this question, I'm asking you, how far did the boat travel during that time? So this is the same question from earlier. So same data chart. Let's see what we have. We say that the initial was 1.50 meters per second. Acceleration was 2.40 meters per second squared, and t is equal to 5 seconds, and x initial, or x naught, is equal to 0 meters. Now, wait a minute. If you're saying, Mr. Lee, when did you give us that? I'm going to tell you this. If I don't ever give you the initial position of an object, assume that it's 0. Make your life easier. Sometimes I'm going to tell you where it started to make your life a little bit more hectic. But if I don't give it to you, make it 0. Alright? And in this question, I want to find out how far it went, the distance, the x. So once again, we'll start off by writing our equation, which we see here. Bloop. Alright, Alright, there it is. X is equal to x naught plus v0 x t plus 1/2 at squared. Alright, so let's plug in the variables that we know. Here, v initial, we have 1.50 meters per second. Let's put that in right there for v initial x. Okay? Now we have 2.40 meters per second. That's acceleration. Plug that in right there for acceleration. Now, remember, we're separating each variable with parentheses. T for 5. Plug that in for t. Now, a lot of my students ask me, Mr. Lee, do we square this entire thing? To which I will respond, no. Just square the t. Okay, if we want to square the entire thing, it will be in parentheses. Alright? And x initial is 0, so we're going to put that in there. Uh-oh, I'm messing up. Alright. We're going to lower that And if your equation looks something like this, you're off to a good start. Now all you have to do is, oh boy, learn how to use your mouse. At this point, just plug it into your calculator and get the answer. So I'll pause. Did you get it? Did you get the answer? If you got 37.5 meters, congratulations, you're one more step closer to getting a awesome physics degree after you go to college, because you'll learn about all this stuff. Alright, next. Kinematics number 3. New problem. So let's get situated. Now, one thing I like to do is I like to draw these problems down. So if you want to pause and read the problem and draw what's happening, you know, if you're like the artsy fartsy visual type of people, okay, please do so now. Anyways, and we're back. So you're driving through town at 12 meters per second when suddenly a ball rolls out in front of your car. Who's throwing this ball? Probably some little 5-year-old. So you have to immediately put on your brakes and begin accelerating in the opposite direction at 3.5 meters per second squared. Now, if you haven't seen my acceleration video, stop this right now and go back, because I want to tell you that there's no such thing as deceleration. It doesn't exist. It's just a word used to describe accelerating in the opposite direction. Never say deceleration. It's bad. It's bad for you. It gives you pimples. And with homecoming coming up, you don't want pimples. So don't say it. I feel like I'm breaking out right now because I'm saying it so much. Anyways, the question is asking you, how far do you travel before coming to a complete stop? Once again, write down everything you know. I know, and I hope you know because it's right there in front of you, that the initial is 12 meters per second. Right there. Alright, highlighting. Acceleration is negative 3.5 meters per second squared. Now if you're scratching your head and saying, Mr. Lee, what did that, where did that negative come from? What is that negative doing there? Well, I'm going to answer, well, duh, opposite means negative, so that's where that negative came from. Duh. Alright, anyways, we know that, you came to a complete stop, which means that if you come to a complete stop, are you moving? No, you're not moving, so if you're not moving, what's your velocity? 0, and that's where I got this little bit of information right there. Now, decoding these word problems might take a little bit of time, but you know, eventually we'll get there. What do I want? X, the distance. Alright, so let's figure it out. Start off by writing your equation. Always start off by writing your equation. Don't be lazy. Don't skip steps. There we go. After you do that, let's take a look here. Sneak peek, sneak peek. Okay. Plug in all the variables that you know. Alright. Remember, use parentheses to separate variables that are together. Last but not least, oops. Okay, this is what we get. Alright. And then we do some fancy algebra to get distance is equal to 20.57 meters. It's so beautiful how the negatives just cancel out. Alright, next. Here I'm gonna put a little slide here and say, whoa, Mr. Lee, 3 equations, I don't know which one to choose. Well, let me tell you what. After you read the question and you create your table of your knowns and your unknowns, here's a little tip. On every equation that you have all of the information except for one is the equation you're going to use. Okay? If there's an equation where you don't know 2 or 3 things, don't use that because you're not going to be able to solve it. If there's an equation where you don't know one thing, choose that equation, okay, after you figure out all the variables. Or you could just use this handy dandy chart, which I won't give you because I think it's simple enough. Alright, now, sometimes things are going to go up or down, as we know, and that's in the y direction. Okay, now if it goes in the y direction, every time we see an x, all we have to do is replace that x with the letter y. Why? Because that's the way it goes. And here we have the 3 kinematics equations rewritten to have the y variable instead of the x. So if you feel like you have to copy this down, please do so. Alright. Okay, so with those three new quote-unquote equations, here's another example problem that we can use. All right, a stone is dropped at rest from top of a cliff. It is observed to hit the ground 5.78 seconds later. How high is this cliff? All right, so let's think. If you are dropping a stone from rest, is it moving? If it's resting, it's not moving, right? If it's at rest, it's not moving. If it's at rest, it's not moving. So with that, if it's at rest, it's not moving. Now the reason why I'm saying this so much is because that little phrase right there really confuses students. Keep that in your head. Now, if your initial y velocity is 0, we're going to write it down as initial as y is equal to 0. Gravity or acceleration due to gravity is 9.8 meters per second squared. Y initial, where you start off, we're going to call that 0. Remember, if I don't tell you how high up something is, consider it 0, or where you start, consider it 0. And of course the time is right there. What do we want to know? The height of the cliff. Alright? Which variable is not given and not asked for? Alright, let's think about that. Which variable is not given and not asked for? Uh-oh. The answer to that, ladies and gentlemen, is the final velocity. So are we going to be looking for the final velocity? No, I hope you're saying no, because we're not looking, we're not looking for the final velocity. Alright, so knowing that, we want to find y. So using this equation where we have y initial, we have v initial y, we have g for gravity, and t for time, we can fill in everything to figure out what the y is. Now you might have gotten a glimpse of the answer. Right here it is. This is the initial setup. Now you might be asking yourself, Mr. Lee, what about this y initial here? Why don't you put that down? To which I'm going to reply, because that's just a 0. Alright? If you're adding 0 to something, you're not really adding anything. So if there's nothing there, I'm not going to waste my pixels on it. Alright? Plug that into your calculator, solve it in your head, and we get y is equal to negative 163.7 meters. Alright, so what does that mean? That just simply means it fell 163.7 meters, so that must mean that the height is 163.7 meters.